just now we already introduced some of the calculation like the divergence, the curl, and also two related theorem called the divergence theorem and also the Stokes theorem. Yeah, so now we can try to derive the differential form for the Maxwell equation. Actually, there's a story about this Stokes theorem. At that time, Stokes is a professor teaching the mathematics, and at that time there is a exam. So this Stokes tried to give this theorem as a question for the students. And at that time, only one student can prove it correctly, and the student is called the Maxwell. So, and Maxwell used this one to really propose the Maxwell equation. So it is a related story about the Maxwell equation, the Stokes and Stokes and Maxwell. So here, just now we have a Gauss law. Originally, we can write it as the double integral of the E field, the closed surface integral of the E field equals the Q in charge, Q enclosed over epsilon naught. And actually, this Q enclosed can be written as a triple integral of the charge density So we can actually use the divergence theorem, which is try to link the surface integral with the triple integral. But the difference is that on the left-hand side, we only have this E field, but on the right-hand side, we have the divergence of the E field. So in this case, so this is the left-hand side of the Gauss law. So this one is equal to the triple integral. And of course, this one should be equal to this term. So we have the expression like this. And we know that this triple integral and this triple integral are for the same area. And this area, this volume can be arbitrarily chosen, which means that in the whole space, the integrand itself should equal to each other. Otherwise, if we take arbitrary volume, then the triple integral won't be the same. So which means that we should have this integrand equal this integrand, which means that the divergence of E should be rho of E naught, rho over E naught. So this is the differential form of the Gauss law for the electricity. And similarly, we can also get divergence of E equals 0, because for the other Gauss law for the magnetic field, which is like the surface integral of the B field equals 0. So on the right-hand side, it is nothing but 0. So it turns out that divergence of B is 0. So for the Gauss law, it will be easier. And for the Faraday's law, you can see the Faraday's law is like the line integral of the E field equals the derivative of the magnetic flux over with respect to time. So this magnetic flux can be written as the double integral of the B field. And using the Stokes theorem, we can have this line integral equals to a double integral. But on the left side, we have E dot ds, but on the right side, we should have the curl of E. We should have the curl of E. In this case, so this one equals this one. And actually, this is the left-hand side of the Faraday's law, which means that this one should be equal to this one. So we have this one, which is here, and also this is the derivative of the magnetic flux to be here. And actually, we can just put this one into here. We assume that these two can be exchangeable, but we need to change the full derivative into a partial derivative for this term. So finally, we can see that this is a double integral. This is another double integral. And likewise, it should be satisfied for different surface, which means that the integrand itself should equal to each other at every point. In this case, the curl of E should be the negative partial B partial T. So this is the differential form for the Faraday's law. Differential form for the Faraday's law. And similarly, for the Ampere's law, we can write it like this. So this is the V dot ds, the line integral of V dot ds, and then this is the static current, and this is the displacement current. So using the Stokes theorem, the left-hand side will be equal to curl of B, and then surface integral of the curl of B. So in this case, this one equals to the right-hand side of the Ampere's law. And yeah, and actually we can just put this mu0 inside. So we have mu0 times J plus mu0 epsilon 0, and then we also put this one inside. So we have partial E partial T here, and then we have mu0 epsilon naught. This is the displacement current, and then this is a static current. So if you like, we just plug this one inside the double integral, and then actually the surface for these two are actually the same, so we can just merge it together within one surface integral. And we can see that this surface integral and this surface integral also share the same surface, which means that all the integrand should be the same at every point. Which means that the curl of B should be mu naught J plus epsilon naught partial E partial T. So actually, this is equivalent to the displacement current density, something like that, because this is the static current density. So this should be like the displacement current density. And this is actually the differential form for the Ampere's law. So by using the divergence theorem or the Gauss theorem, we can derive the differential form of the Gauss law, and also we can make use of the Stokes theorem to derive the differential form of the Faraday's law and also the Ampere's law. Be like that, yeah. So actually, yeah, the differential form will be more useful than the integral form, because for the integral form you can only calculate some symmetric structure, and actually even calculating the whole surface integral will not be so useful, because usually what you will concern is the electric field at a specific point, and the differential form can help you to do that by making use of some numerical method. You can just solve the E field and B field in the whole space. You don't necessarily want to find some Gaussian surface or some Amperean slope to calculate some of the double and or line integral like that. Okay, so now we will consider the conservation of charge. The conservation of charge, yeah, so the conservation of charge, you can consider it like the charge cannot be created or vanish. But actually, if we would like to represent the conservation of charge with one equation, it should be like this partial rho partial t plus gradient of J equals 0. Gradient of J. Yeah, so gradient of J is like the current, something like the current. So which means that within a volume, if the density is changing with respect to time, if it is increasing, which means that there should be some current going in this volume to make the charge density to increase. Otherwise, if this rho is decreasing, which means that there should be some J flowing out from this region to make the charge density decrease. So we have the plus sign here, which means that this is the charge going in or going out. But generally, we have the plus sign for going out and negative sign for going in, which is actually the same. So we have plus sign here rather than having partial rho partial t equals gradient of J. This is not correct, because if you want this to be if you want partial rho partial t to be a positive value, which means that you would hope the J to be going in rather than going out. So we should have a minus sign here to make everything correct. And if you just move this term to the left-hand side, you have partial rho partial t plus a gradient J equals 0. So this is called the conservation of charge. And yeah, of course, we can also rewrite this rho and also J in the double and triple integral. So the I is actually the double integral of J with a minus sign here. So we can write the current to be the surface integral of the charge of the current density. And here we make use of the divergence theorem. We make use of the divergence theorem. So that this surface integral is actually the same as the triple integral, but with the divergence to this vector field. And of course, we have a minus sign here, so we just put this one inside. So actually, the current is nothing but this triple integral of this minus divergence of the current density. So this is I, this is J, yeah, so like that. And also, we know that I is the derivative of the charge. I is also the derivative of the charge, which means that the charge can be also written as a triple integral of the current density So in this case, if we plug in this derivative inside the triple integral, we need to write it as a partial derivative. So it will be like the triple integral of the partial rho partial t dv. And in that case, these two are I, so which means that these two are actually the same. And these two triple integral specify the same volume, which means that the integrals will be the same, which means that these two are the same, so the integrand are the same. So it turns out to be partial rho partial t equals minus divergence of J, or you move this term over, so you have partial rho partial t plus gradient J to be 0. So this is actually the conservation of charge. And if you would like to have the Maxwell equation satisfied, yeah, you can see that actually the Maxwell equation will satisfy this conservation of charge if the Ampere's law include both terms on the right-hand side. So actually here, For the Ampere's law, it will be nothing but this term, the curl of B equals mu naught J plus epsilon naught partial E partial T without this divergence. Actually, we can take the divergence on both sides, so that the left-hand side will be the divergence of the curl of the magnetic field. And then we can also apply the divergence on the right-hand side, so that it will be like mu naught is a constant, so this divergence directly act on the current density. And for the second term, epsilon is also constant, so the divergence act on this E field. Yeah, so it will be like this. And if you just check on the mathematics, you can see for any vector field, if you take the curl and take the divergence one by one, then it must be a zero. It must be a zero, because it is like, for the curl, it is like you see how the vector field are rotating, and for the divergence, you check the vector field whether it is going in or going out. So after you checking the rotation, and then you check the flow, then it must be zero. Then it must be zero. So you can try to prove it if you are interested, or you can just find this identity on the internet or on the Wikipedia. So actually, this is a theorem called the divergence of a curl is zero for any vector field. So which means that this term is zero. This term is zero, and we can see that this one we can use the this one is the left-hand side of the Gauss theorem. Left-hand side of the Gauss theorem. Actually, the Gauss theorem is like this. So we can just plug in this one into here. Plug in this one into here. So we can see that for this theorem, we can plug in zero on the left side. So we have zero here, and then mu naught divergence of J plus this one, epsilon naught multiplied by this one. And you can see here, divergence of E is a rho over epsilon naught. So you just plug in that term here. You have epsilon naught partial T, and then rho over epsilon naught. So epsilon naught and epsilon can be cancelled. So you only left with the partial rho partial T. And this is actually the conservation of charge, which means that this side is zero, which means that the Ampere's law with these two terms will be compatible with the conservation of charge. If we only have one term, it is not really satisfy the conservation of charge. If we have further the third and the fourth term, then it cannot satisfy the conservation of charge either. Only with these two terms, it will be the best option. Yeah, so this concludes the supplementary for the chapter 32.